Why did you want to be an astronaut?
Well, I have to admit, I grew up watching a lot of Star Trek with my dad, and he was a space fanatic. This was in Montreal, and the space program was budding, and he would also see the pictures of Mission Control and say, who are those guys? How do they get to work there? That's got to be the most amazing job in the world. And the funny thing was, for me, my dad said that he knew Captain Kirk because he knew him from high school in Montreal. And so at that age, I was probably 5 or 6, and so it was a strange mixture of fiction and reality. Like, I knew this was fiction, but on the other hand, my dad knows this guy, and somehow that maybe made things seem more possible to me. I don't know. But then we went on a family vacation to Florida, and it was the time of Apollo 11, so we got to see the launch of Apollo 11 on a family vacation there. I was 6, and that was it. I told my dad at that point I wanted to do that, and never changed my mind.
I want to get you to take us through that story. I want to start with your hometown or hometowns. Tell me about where you grew up and what it was like there.
Well, I grew up in Montreal originally until I was about 11, and then moved to California. My dad felt that California was the land of opportunity at the time, and he was probably right. And in both places, we also had like a really small country house. So a lot of my memories are spent spending time around a small lake and swimming and boating and things like that, and playing around in the woods. And also, I was in Scouts, so I think a lot of my childhood memories are camping and backpacking and spending time in the mountains, and some of that's with family and some of that's with friends. And but I grew up in San Jose. Basically, went to high school in San Jose, California, and when I was there, I think most of the inspiration, I think, for me was from my parents and my teachers.
So you do have a sense that the people in those places and really helped make you who you are.
Yeah, my dad was a mathematician and a quality control engineer, so he was kind of a perfectionist. So I'd come back, if I got a 97 on an exam, he would say, what happened instead of that's great. And an interesting thing I think for me coming from Montreal to California was that and it's kind of a reflection on our education system and why it's so important that we try to improve it. And that I was 3 years ahead in math coming in 6th grade from Montreal. So much so that they didn't have a book for me at the elementary school. And so I spent the rest of that year tutoring, like the kids who needed help in math, which is kind of formative for me because I kind of tutored the rest of my time through school and college, and then taught later, after I finished school.
So in 6 months in space, did you get a chance to see Montreal and San Jose?
Yeah, that was a really neat moment for me on the space station. It was one day, and I think it was pretty early on in the mission when we were flying over North America, and having grown up in San Jose as a teenager and in Montreal as a young boy, all my memories, from childhood took place in basically those places. And places in between on trips. My family took across the country, camping trips in the Sierras, or so all the places that I had been, I got to see them in about 3 minutes. So like every place I'd ever been and everybody I knew and all the memories I had, I could just kind of look down and relive them all in about 3 minutes, and it was unbelievable.
That's not the same as your life flashing before your eyes.
Not exactly.
No. Let's tell me more of the story. Give me the sense of your educational and your professional career that ultimately led you to become an astronaut.
Well, after high school, I went to Cal Poly, San Luis Obispo in California. I started off in physics, and I really was excited about physics, but I really liked robots for some reason. I think part of it was the idea of it was kind of it was a new field at that time, really, and I kind of liked the idea of programming logic that comes out of your head into a system, and then watching it, live in the sense and act on logic that you gave it. In other words, I suppose it has this sense of creating life in a way, because it, you give it something and then it uses that and operates from there. And so I changed over to electrical engineering, and so and my senior project there was a robot. First one that I had made, and that was really pretty cool. Did it with a roommate who was also in mechanical engineering, so he did all the mechanical engineering part of it. And but during college, there was two things that happened that really were meaningful to me. One was that it was during my freshman year. It was the first flight of the shuttle, and I just remember so vividly being in the dormitory. People gathered to watch the first flight, and for me, I'd wanted to do this all my life, but there wasn't there yet wasn't any urgency or sense of direction, of how to do it. And as soon as that happened, I said, I got to call NASA and ask them what I have to do. So it's the first time I reached out and tried to find out who at NASA could tell me what to do, and found the astronaut selection office. And heard back from them, and they kind of give everybody the same advice, which is be the best you can be at whatever you choose to do. Don't focus your career on trying to do this, but just be the best you can be, and follow what your interests. And so I never got a B again in college after that. I couldn't allow that to happen, and so that worked out well for me. And in the end, at graduation at Cal Poly, so now this is the end of those 4 years, another thing happened. And so in between, it was just college, and I had a good time and worked hard, and made a lot of great friends, lifelong friends. And at the end, graduation, there was our graduation speaker was an astronaut, the first one that I ever met. And that was Hoot Gibson. And I didn't know this was coming. It just suddenly there was an astronaut talking at our graduation. And because I did so well, I got to go up to the podium to get an award. So I got to, and instead of walking back to my seat, I turned around and walked toward him sitting on the stage to shake his hand. And later on, I got to remind him of that. He remembered it because it was kind of out of order to do that. And so that was a really neat kind of inspiration. That kind of bracketed my college education was, seeing the shuttle first go and then an astronaut at the end, and that really focused me in college. Then I went to Caltech after that for a master's. Kind of turned to aero. I mean, I always was interested in aero, but electrical engineering was also. I grew up in Silicon Valley, so this was the job security path as well, and the field my dad was in essentially, and but turned toward aero. Did a master's in aero at Caltech. And maybe at Caltech, the thing that I kind of learned at Caltech is, there's a lot of brilliant people in this world, and I wasn't one of them. There's people who are brilliant, and there's people who have to really work really hard to achieve, and I'm in the second category. And then I went to MIT after that for the rest of my graduate work for a PhD, and the really neat thing about being there was. I was working at Draper Laboratory as a research assistant while being a grad student, and I got to work on NASA programs for the first time. So the Hubble telescope, I got to work on analysis for that, for the release of it from the shuttle, and I got to work on the shuttle autopilot, and I got to work on space station later, and so I got to work on real NASA programs, which made me feel like I was getting closer. And then after I finished graduate school, I taught in my wife and I. My wife was finishing medical school, and we decided to spend a couple years doing something different. So we went to Sydney, Australia, and I taught in the university there, aeronautics for a couple of years, but the whole time I was applying to NASA, for 10 years, and finally got interviewed, and then after getting disqualified for a medical condition, which was devastating, that cleared up, and then I got in 2 years later after already coming to Houston. So I worked in Houston for a couple of years as a flight controller before getting selected. So that was the path.
The flying in space part of the job that you worked so long and hard to get is a part that that has its dangers. There's no denying that. But Greg, what is it that you feel we get as a result of flying people in space that makes it worth taking that risk?
Well, there's no, you know, there's a saying, there's no reward without risk, and you know, and also, you know, if it's worth doing, it's worth doing well. And I think from NASA's perspective, that means doing it safely, you know. And so we take measured risks, you know. I mean, you know, what we do, we believe in, we think is very important, and we do everything possible to make sure that there's backups and redundancies and checks to make sure that it's as safe as it possibly can be. But having said that, you know, yeah, there's certainly an element of risk, and you know, it's sort of the sense of, you know, you know, it's part of human nature to explore and be curious and want to know new things. And my kids are 5 right now, and it's neat because it must have been a teacher that told them, you know, that you know, we do science because we're curious, you know. So they say, I'm curious, I'm going to be a scientist, you know, which is really cute. And you know, and you know, the science and exploration, I mean, that's what it is. It's, you know, we're curious, you know, species, and we want to understand things, and that's what our exploration is all about. And you know, I feel like we're kind of living, you know, once you've been in space and you can look down on the Earth and see the whole Earth floating, you know, in emptiness with your own eyes, you really get the sense of this is a small part of what there is to know about, you know, and it's so important, and we've explored it, you know, quite thoroughly, and there's still plenty more to, you know, to learn and explore on Earth, but there's so much more out there. We just have to be out there, you know, exploring it, and you know, I think it's just it's destiny. It's our future. We have to do it, and this is the beginning of it. And you know, it's very exciting to be part of it, and I wouldn't want it any other way.
Greg, you're a member of shuttle mission STS-134's crew. Could you summarize the overall goals of this mission and tell me what your major responsibilities on this flight are going to be?
Sure. Yeah, I think probably the most significant thing on this flight, without a doubt, is the AMS, the Alpha Magnetic Spectrometer that we're flying up. This is a physics experiment. It's a $2 billion experiment built by 15 countries, and this will be installing this on top of the space station. And there's no doubt this is probably going to be, you know, one of the most significant contributions to the science on the space station in the years to come. So that's a very big part of the mission, is getting that installed safely and correctly. And in addition to that, there's a platform we have. It's called ELC-3. It's a logistics platform. It goes outside also. It gets installed on another part of the truss, and it has spare equipment. Basically, there's a list of equipment on it I could give you, but essentially it's there to enable us to keep flying the space station, you know, for the next 10 years and have the spare equipment that we need. And then we have a series of spacewalks on the mission. I'm excited to be doing a couple of those. And some of that is maintenance, some of it is science related, some of it is installing some new equipment. And so I think between those 4 spacewalks and all the robotics operations to install the 2 big payloads that come up in the payload bay, those are the priorities of the mission.
Almost everybody on this crew has been to the space station before. In fact, you and Mike Fink have had long duration stays on the station before. Has that really benefited the group of you as you prepare to fly STS-134?
Oh, I'm sure, you know, we all feel that it has, and a lot. I'm sure, you know, in the training, it makes a huge difference because we know exactly what to expect. You know, I think, you know, as you say, especially for Mike and I, you know, we were up there. Actually, we overlapped for about 6 weeks. We were there together, and during the time that I was there and the time he was there were multiple shuttle missions coming and going. So the whole dynamic of a shuttle coming up to the space station, the 2 teams working together, you know, how the space station prepares for us, you know, which I did for another shuttle, how we work together when we're up there, and then of course using all the systems on the space station, in our case especially the airlock on the space station, you know, for the spacewalks. So all that is so familiar to Mike and I. It helps throughout the training because we can bring up, you know, these points that are relevant, you know, as they come up for the shuttle crew that hasn't necessarily seen all these things. And Roberto too. Roberto, you know, has been there on Soyuz twice, so he's also got that same familiarity with it, with the space station. So it helps a lot. The training, I know during the mission, is going to make things go a lot smoother. And we'll know how to treat the space station guys because we know how we would like to be treated when shuttle crew came up and we were helping them. And so it's a really helpful thing. I think it's great. And we're looking forward to seeing the space station again. I can't wait to see it again.
Well, yeah, you've done 6 months on the station, so now you're looking at going for just a shorter period of time, but you're also going to a station that's changed since you were there. So what are your expectations about what you're going to see when you arrive?
Yeah, I can't wait to get there again. You know, like I say, it was home for me for 6 months. You know, and I feel that way about it. It's a place I've lived in my life for a significant chunk of my life, and so I can't wait to see it again. And it has changed. The one big change I think that I'll notice is the cupola window. You know, every window that I had when I was there was a porthole window. Some were beautiful. The lab window and the windows in the gem that are out the side in the Japanese module were spectacular windows. But the cupola, you know, you can move into it and have windows all around. It's a 360-degree panoramic view. That's going to be spectacular to see that. And there'll be additional modules. It'll be even bigger, you know, even harder to find somebody than it was when I was up there. And the other thing, when I was up there before, I had, you know, we were ready to do spacewalk if we needed to. And I had a suit ready, you know, for me there that I bumped into as I flew past it every day, and did a lot of work in the airlock, but never had a chance to go outside. Nothing broke. You know, we're kind of in a funny way hoping for something really small and simple to break so we could go out and fix it. But so I'm very excited this time to get a chance to actually go out the hatch and see the outside of the space station. So I can't wait for that.
Let me get you to tell us a little bit more about the stuff that you're bringing. Express Logistics Carrier 3 you referred to before. Tell me what its function is on orbit.
So this is basically a platform that sits in the shuttle cargo bay, and it'll move and it'll be installed outside on the truss on the station. What's on it is things that have to be outside or will be used outside, spare equipment. One thing is a tank, a high-pressure tank for the airlock. Another thing is a spare part of one of the robotic arms. It's called SPDM, Special Purpose Dexterous Manipulator. It's part of the Canadian robotic arm system, and it's a spare manipulator for that. There's some extra antennas on it for our S-band radio, and so there's spare equipment on this platform that we'll be installing and setting up. One of the spacewalks will involve making sure some of that equipment is ready to be used when needed, and it'll be out there, you know, for the next 10 years, you know, and you know, as needed, equipment will come off of that platform to be used to replace things as they wear out.
So it's not anything that we have to have right now. It's
That's right.
Prepping for stocking the pantry.
That's right, exactly.
How does it go from getting in the payload bay out onto the truss? What's the procedure for getting it out?
Well, the procedure's all robotic, and a lot of us on this crew are involved to make this all happen. Two guys, in that case, I believe it's Mike and Roberto. They'll be doing the shuttle robotic work, so they'll take it out of the payload bay with the shuttle robotic arm, and they'll basically bring it out and put it in a position where we can reach it with the station robotic arm. Box and I will be on the station side, and we'll move the space station robotic arm into position to grapple it. Once we grapple it, then they can release it. It has to be in that order. and then we'll move it into position to install it on the truss. On the truss, we have these mechanisms for attaching external payloads. And they basically have guide vanes, so you can bring it in, you know, and they have targets and camera systems, so you could steer it in, you know, perfectly. And so we'll be doing all of that. And then there's basically a big claw that you know, once the mechanism for the claw is in operation, the claw grabs a capture bar and then pulls it down and pulls it tight and holds it in place. So if everything works right, you know, that claw will stay closed and it'll be solidly attached, you know, forever at that point. And there's also some electrical umbilicals that have to connect to it, and so another motor mechanism has to move into place and provide power, data communication to everything that's on the platform. And so Box and I are taking turns. In that case, I'll be flying the robotic arm, and he'll be doing the mechanisms on the attachment system. And then on the next day, we'll do a similar thing for AMS, where we'll swap roles.
So for AMS installation, you'll be on the station arm side as well?
Yeah, so it's for AMS installation, again, on the shuttle side, and this time I believe it's Drew with Roberto flying the shuttle arm, moving AMS into position with very similar thing, different position, different side of the space station. So from the robotic team's point of view, everything's different. But from our point of view, you know, it's a similar, you know, or from a generic point of view, it's quite similar. And that station arm grabs it, puts it into place, mechanisms grapple it, pull it down, and so it takes quite a few hours. It's a tricky operation. The tolerances are really tight. You don't have camera views that show you clearances between things that you would like to know for sure that you're not hitting. So it takes some training to make sure we know exactly what we're expecting and get it in there right. And but if all goes well, it should be no problem. I have to say for the AMS, which is the very expensive payload, the one that's most important, the attachment mechanism we're putting it on doesn't have the same level of redundancy as some of the other attachment mechanisms. In other words, there's not two motors if one fails for attaching it, for example. So I'll be breathing a little better after that's been completed, and I know that it's attached successfully, just because I know we don't have the redundancy there, if something does go wrong.
Is that a possible contingency EVA task that you guys have prepared?
There's some potential tasks we could do. There's a couple of fallback things we can do, and it's possible to keep the AMS on the robotic arm overnight if we have to do that. It can provide power to it through the robotic arm. So yeah, we have some backup plans. Hopefully we don't need them.
Right. Fill me in on the alpha magnetic spectrometer. What does it do once it's in that position out on the station's truss?
Well, this is an amazing instrument. The AMS, as you said, alpha magnetic spectrometer. In my mind, this is like the Hubble Space Telescope. I mean, it has the same type of potential for revolutionizing our understanding of the universe. It's looking at cosmic rays, so it's different than a normal telescope. And as it's collecting cosmic rays, it's basically able to measure mass, the direction they came from, the energy they have, and whether they're also matter or antimatter. And so I think, fundamentally, it's designed to look for antimatter and dark energy, dark matter. But it's looking at all cosmic ray particles. And the thing is that on the ground, they've been trying to simulate or create, different nuclear particles with these accelerometers. Accelerators, nuclear accelerators, and the energy levels that they've reached on the ground are still, order of magnitude or more or less than what's in free space. So it's possible that they're going to see things that, first of all, they'll see the natural background distribution of these kind of particles, and they'll see possibly some ones that have not been able to create in the laboratory. So there's a lot of potential for discovery. And the other thing is that it knows where the particle is coming from, because if it could be pointing at a galaxy, and if antimatter particles start showing up in the detector, it could be telling us that galaxy is an antimatter galaxy. And the whole universe was supposedly, in the Big Bang Theory, made in equal parts antimatter and matter. But now what we see is essentially all matter, as far as we know. But it turns out that this thing can detect antimatter particles at a certain level. It'll help us understand the nature of the evolution of the universe. So it's some pretty interesting things. And also I think the thing that Hubble did for us that was one major thing Hubble did for us was very interesting was we knew that the universe was expanding, and we wondered whether or not there's enough gravity for it to stop expanding and recollapse, or whether or not it would expand forever, And Hubble figured out that not only is it expanding, but the rate of expansion is increasing. And how does that happen with normal gravity? So there's something else we don't understand, and and that has to do potentially with dark matter and dark energy. And so if AMS helps us understand these things, I think the concepts of antimatter, how antimatter and matter work, and how gravity works, these are fundamental concepts we still don't really understand. It doesn't fit into the grand unified theory yet. And just like when we figured out electromagnetism, we have things like TVs and communications and satellites and all this technology based on our understanding of electromagnetism. And so I think this is the beginning of the next phase of understanding physics that could really be important for the future. So it's pretty interesting stuff that they're looking at. It's fundamental physics, but in the long run, I think it has great potential for pushing us to the future. So very interesting stuff.
And in this case, as I understand it correctly, the station is used as a platform for AMS, but the crew members on board don't really have anything to do with it, helping it take its readings or measurements.
Right. It collects an incredible amount of data, and it's looking at you know, all the particles coming through the detector, and we're talking, you know, many particles per, you know, let's say nanosecond or whatever, and it's figuring out which ones came in the right way and left the right way, so they can match up, you know, that the one that left through this surface was the one that came in through this surface. So it has a lot of there's a lot of analysis to do to figure out, to match up, you know, exit and entry points, and you know, figure out the curvature of particles in there and figure out the mass. And so a lot of that raw data goes down to the ground. There's some onboard computation and data compression, and then it all goes down to the ground. And there'll be terabytes and terabytes and terabytes of data for physicists to analyze for the next 10 years.
Keep them busy for a long time.
No doubt, no doubt.
You mentioned a few minutes ago that the plan for this mission also calls for 4 spacewalks by 3 different teams of spacewalkers. Tell me what your role as a member of this team is going to be on this flight.
Sure. You know, this is a really exciting part of the training and preparation to just being part of this team. As you said, there's 3 of us. So Drew Feustel, he's going to be the lead spacewalker, and Mike Fink and I. Mike Fink's done several spacewalks on the Russian segment before. For me, this is the first time. And the 3 of us work in a team for all the spacewalks. So 2 of them on any particular spacewalk, 2 go out the door. The other one works inside. We call him IV, and those guys EV. And the IV is the sort of taskmaster, the one who's keeper of the master plan. You know, okay, next we're doing this, next you're doing this, and you know, and as things evolve, you know, if they change a little bit, is the one who's keeping track of everything, and also communicating with the ground, and being the interface between, you know, the crew and the ground, and the plan, and you know, how well the suit is doing, and how much time we have left, and everything. And we just kind of rotate that. So on EVA1, I'm out the door with Drew, Mike's IV, and then EVA2, I'm internal, I'm IV, and those 2 guys are out the door, and we rotate that way through all the spacewalks. So in combination then with the ground team, you know, we have a whole team of folks that have been working on us now, you know, by the time we fly, it'll probably be 2 years, you know, that they've all been working on this. And so it's a really neat team of folks really focused on making all this happen. And you know, who knows if we'll execute it exactly as planned, but you know, we train to be able to be flexible. And but it's exciting to be part of that team, and I like the way that teamwork works. It's a little different than the experience I had before training for space station, because I was flying with 2 Russians, and a lot of my training was solo. So it's a neat difference in the training to be on a team like that.
It gives you a bit wider experience for your future flights.
Exactly.
Well, let me get you to tell us about what's going to happen. Let's start with EVA number 1. You and Drew are outside. What's on the timeline? All
right, let's see. So on EVA 1, so Drew and I go out, and this will be my first time out the door. And so the first thing I do is this thing they have a funny name for, translation adaptation, because we're so used to training underwater. And you know, underwater, you know, it helps. You get a sense of you know, 0G and a sense of orientation. Of course, gravity is still there, but the water resists your motion, so it takes effort to move and very little effort to stop, because you have the water helping you stop the motion. And in space, your expectation is that, you know, that yeah, it takes work to stop too, because there's nothing slowing you down. So, if I have a couple minutes to do that, make sure I don't go flinging myself off the station because I pushed too hard. While Drew sets up a couple of tethers, and then the main things we're doing in this task is that there's an experiment called MISSY. It's a space exposure experiment. Basically, they're like large suitcases with lots of samples inside it. And those samples can be everything from materials to paints to coatings to electronic equipment to biological samples, and they could come from different organizations. And the idea is to expose these things to the harsh environment of space for a long period and see what happens. You know, see if the seeds will still germinate. See if a paint material will protect, you know, what's below it. See if a circuit can still work. You know, and to help us design better systems for the future. And so there's 2 experiments out there that are part of MISSY 7. We're going to retrieve those, close them up, take them back, put them in the shuttle cargo bay, and then we take new ones out of the cargo bay, MISSY 8, and we install them up on the truss, and they'll be out there for 6 months to a year before they come in. So that's the first main task.
Does this give you an opportunity to crawl way out on the end of the truss?
Oh, not way out,
okay.
but that comes later.
Okay.
Yeah. So we do that, and then the thing that part of this 4 EVA sequence is refilling a radiator that's out on one side. And to do that, we have to sort of connect a lot of ammonia hoses between a lot of segments, including one that jumps across the rotating solar alpha rotary joint, which normally can't have a hose running across that's connected to both ends because it has to spin freely. So we're going to go out and we're going to connect all these hoses and then vent them, basically, so that they're filled with N2, nitrogen. We're going to vent them so that they're ready to be used for the ammonia fill on the next EVA. So that's another task. And then and we connect them all, and we disconnect the part that jumps that joint so that the joint can still spin freely. And the solar panels are out here. They have to be able to continue rotating. And also on this spacewalk, we have there's some external, it's kind of like your wireless hubs in your house, you know, or a network. It's basically a couple of antennas that enables a wireless system to be working outside the station. So there are experiments and payloads outside the space station that need to communicate to the data system. And we're installing a couple of antennas and all the wiring for that to enable those pieces of equipment or experiments, whatever, to communicate to internal systems through those antennas. So it's a lot of wiring. It's a little messy with long wires, and it takes a while, but that's going to be in the front of the space station near the shuttle. And the thing that's maybe a little interesting about that is just that in order for us to do that, they have to disable some things, you know, internally we may lose communication. So and we may have to like wave through the window and say everything's okay, and then go down and finish the work and come back and say everything's okay. So we'll see how that goes, but it should be interesting.
As you mentioned, 2 days later, you and Mike swaps places. Mike and Drew go outside on the second spacewalk. What are they going to do out there?
Yeah, so this is a very interesting, challenging spacewalk. There's two major tasks. One of them is to refill that radiator that I mentioned, and so ammonia has to fill these lines, you know, all the way out to the far end of the port side of the station, and while also that's going on, that rotary joint for the solar panel on that side has to be lubricated, and this is a long-term maintenance thing just to make sure that it can go for 10 more years, you know, and not have any friction, you know, with the bearings. But that's a big joint. I mean, it's 15 feet across. It's got lots of covers on it. All those covers have to come, well, not all of them. Some of the covers have to come off. We're going to be inside there with lubrication guns, trying to lubricate different surfaces. There's a lot of connectors to do this. I think we're setting a record for how many fluid line connectors we're connecting and disconnecting in order to set up all these lines to do this ammonia fill and then take it all apart at the end. And the danger is that if it's a minor danger, just that, you know, it could be with one of these connectors that some ammonia leaks out. If ammonia gets on the suit, you know, this is 100% ammonia, unlike the household variety. And so if any comes into the space station on the suit, that's a big problem, health-wise. So we can't bring any in. Now we could bake it out on the suit, but we have to identify it and then go through a procedure to make sure that it's sort of we can scrape it off or have it bake off the suit. So we'll be watching really closely to see if, you know, most likely Drew gets contaminated. If he does, then we'll have to, you know, be out for a certain amount of time to make sure that there's enough time for the sun to bake it off the suit. And there's cleanup steps we can do, and inside the airlock we could check if there's any ammonia as we repressurize. So this is our main concern on this spacewalk, but it's really a ballet between timing, because as we do this fill, it depends on you never want a part of the that segment of hoses, essentially of lines, filled with ammonia without any way to expand out in the sun. So you really want to do certain things at night, you know, other things in the day. And so we're watching the timing, and it's an interesting choreography with that one, just trying to make sure that we nothing is left to expand and have nowhere to go. You know? And in the meantime, Mike will be mostly focusing on the lubrication of the rotary joint. We call it the SARJ joint, solar alpha rotary joint. And Drew will help him as he can. And then we have a couple of other tasks while we're waiting. They're going to rotate the whole joint once they've lubricated it, and then lubricate it again in a different position. And then they'll put everything away. So it's a big spacewalk, that one.
That's a lot of stuff.
Yeah.
And these same two guys are going out again 2 days later. But before they do, they're going to test out a new procedure for purging nitrogen from a bloodstream.
Right.
Spacewalkers have done this, but you guys are going to try out a new procedure.
Yeah.
Tell me about what that new procedure
Yeah,
is.
this is very exciting. You know, I mean, it shouldn't, you know, when you watch a science fiction movie and two people go out the door for a spacewalk, they don't take 48 hours to do it. You know, they just somehow jump in the suit and they're gone. In real life, it takes us a lot of time. And we'd like that to be, you know, faster. For example, on the first spacewalk, we're doing camp out, which is one of the normal things we do on the space station, is we go into the airlock the night before, we depressurize the airlock down to 10.2, 14.7 is a normal atmospheric pressure, we're down at 10.2. We breathe some oxygen off masks in that process, and we sleep at the lower pressure. And it's just like scuba diving in a sense. You know, what you're trying to do is get nitrogen out of your body, out of your bloodstream, you know, and out of your tissues. And that process, you know, by sleeping at 10.2 overnight, you get a certain amount out. By breathing oxygen, that helps that. And then the rest of the process to getting out the door, make sure that when you go all the way out, it's like coming up from, you know, depth. I mean, it's the opposite of scuba diving. In scuba diving, you go down, and it pressurizes, then it pushes nitrogen into your tissues, and if you come up too fast, the nitrogen can't escape and can give you the bends. Here it's the opposite. We're going up first. You know, we're going to a lower pressure first. And so that you would get the bends on the way out, you know, not on the way back in. So anyway, this is the normal process we go through by sleeping overnight in the airlock. Another technique is to do exercise, where, you know, we're breathing 100% oxygen, and we do exercise on a bike, and do a certain prescription of that, which is based on our particular, you know, physiology, you know, body weight and aerobic capacity. And then you know, another sequence of oxygen breathing and pressure changes before we go out the door. So this is a brand new technique that would allow us not to have to spend the night sleeping in the airlock locked up, not have to do the exercise, you know, before. Basically get in the suit and spend a little more time in the suit doing some, you know, with 100% oxygen, doing very small motions, just to make sure that you have some metabolism, you know, going. You're not sleeping in there. You have to be doing something. You're in there a little longer, waiting to go out the door, but you know, overall, the whole process is you know, much simpler, and you can do it on the day of the spacewalk. So we're going to try that on. And a lot of work has been done by a lot of people to make this protocol work out, and we'll try that on the third spacewalk. And if it works great, we can do it on the fourth one too.
Okay, EVA number 3, as we said, Mike and Drew are going back outside. What kind of work have they got in front of them?
So on EVA 3, this is related to setting up. You know, ultimately, it'd be nice if we had the ability to have our robotic arm, which can sort of inchworm around the station. You know, it can grab in one place and work from the other end, and it could also put that end down and inchworm, and then use the other end as the active end to do work. We'd like a base for that closer to the Russian segment. So we're basically installing that. And it's a very big, you know, I'd say contraption in a sense. It's combining Russian and American hardware. So it'll attach to the, you know, to the front of the FGB, the forwardmost part of the Russian part of the space station. So we're bringing that out through the hatch. It's a very big thing. It's got a lot of connections to make, and installing it there, and that'll allow the you know, the robotic arm to base itself in that point, and then do work, you know, closer to that part of the space station. So for the long duration, you know, it's a good thing for us to have that ability to have the robotic arm work there, and I think they have some specific tasks in mind, you know, for that potentially later. And then there's also some additional, I guess you could say, power optimization cabling to do, and that you know, for things that are already working but could fail if a power channel went down, they're not, the power channels aren't optimally distributed, so that you lose the least number of things, you know, if one thing fails. And so there's some cables that we're going to reroute that basically go forward from the Russian segment to the U.S. segment, that changes that improves that. And so it's just a matter of routing some cables and some connectors that are difficult to get to. But those are the main two tasks they'll be doing on that spacewalk.
And much of this work was a relatively late addition to your flight.
Right.
What were the circumstances that caused these jobs to to move back and to end up on your mission?
Well, I think there's a lot of things that are always in flux, you know, and I think as we get closer and you know, by the time we get, you know, I mean, now we're, you know, 4 months from flight, and we think we know what we're going to be doing, but when the actual day comes, you know, it could change, and I think this is one of those things that just became a higher priority than something else, and you know, and also it's a matter of what could be done on previous flights. There was, you may recall, not too long ago, there was a problem with ammonia a pump system on the space station. And the expedition crew, the station crew, was supposed to go out and do part of this spacewalk that we're doing now. And instead, they spent 3 spacewalks fixing this ammonia pump and replacing it, which is, you know, those pumps are expected to fail. We had the spares up there. They had to do the change out, and they did. And it took them 3 spacewalks, and this fell off their plate and fell onto ours. So, and that could happen again before we fly. You never know.
With that in mind, for the last EVA, with you and Mike going out the door, what's on the plan then for you guys on EVA number 4?
So this is an exciting spacewalk for me, partly because I get to ride on top of the robotic arm. So Box will be flying the arm, but what we're doing is we're leaving the boom. There's the orbital, it's called OBSS. It's the inspection boom we have on the shuttle to use to inspect the tiles, and that boom will be left behind on the space station, you know, with the idea that at some point, if the space station has to do some work, it would give the robotic arm more reach if it could use this boom as well. And we have left it up there before. We have the mechanisms in place to leave it up there. So we'll be attaching that boom to the truss, locking it in place. And normally, the shuttle arm grabs that boom at the end, and the station arm has a grapple fixture in the middle. But if we're going to use it on the station at some future point, you want to be able to grab it from the end. So the grapple fixture at the end is not the right kind, and we have to change it. So it'll be kind of fun for Mike and I, because we're kind of tearing this thing apart in a way. We're taking off that end, replacing it with a shuttle, a station grapple fixture. And we have to cut some wires and pull this thing off completely. And while we're doing that, I'll be on the station robotic arm, and Box will be flying me around. So that'll be an exciting task to do. So we do all of that, and when it's done, Mike will be bringing the old grapple fixture back and putting it in the shuttle cargo bay. I'll be doing a couple of miscellaneous tasks, and then we'll meet on top of the ELC platform that we just installed. And I mentioned before, the SPDM, the robotic spare mechanism that's on that platform, they want to release some bolts on that to make sure that it can be utilized when needed. And so Mike and I are going to be up there. These bolts, there's some extra stress on these bolts, so we have a special pry bar. We expect to be doing some, you know, serious manual labor and to try to break this thing free so we can get those bolts off. But the neat thing about being on top of there is that, so this will be the last spacewalk, potentially, of the entire shuttle program in terms of building the space station. And on top of ELC-3, it's sort of the highest perch, you know, above the whole space station. So we'll be on top, looking back at the entire space station that has been built now, you know, by over 10 years by 15 countries and all the shuttle flights. And on this last task, we'll be able to look and see the fruits of all that labor, the whole space station, you know, below us. So I think that's going to be a special moment, and we're bringing a good camera out to take some pictures up there.
Of course, STS-134 is the last flight of the Space Shuttle Endeavour. You have any thoughts about this ship's place in the history of the human spaceflight program?
Well, I think the whole shuttle program, it leaves us kind of with a legacy of incredible amount of experience in space. One time I was with my crew, this crew, and we were in Florida, and we were looking at the cargo bay, and I was just marveling at the size of the cargo bay, you know, from standing right over it, and all the equipment that's in there, and the things we've learned how to do in space. You know, over those 30 years, you know, we've learned how to do so much, from, you know, not just, of course, launching and landing a giant spaceship, but you know, having cameras operating up there, and the rendezvous and the docking and spacewalks and robotics and all this equipment that works in a vacuum, and how to optimize it to work in a vacuum and bring it in and out. And you know, and everything from, you know, from the food that we eat in space now, which is a much expanded menu compared to what it was originally, you know, to how to build a space toilet. I mean, everything in between, you know, all the stuff that has been figured out during the space shuttle program. You know, it's taken you know, science fiction really and made it reality over those 30 years. I think in you know, in the early days, the things that we did before the shuttle were magnificent, and you know, even though we haven't been back to the moon yet and we haven't gone on to Mars and further out yet, what we have done is learn how to get an incredible amount of hardware and complex hardware in space and operate with it. And so I think that's, you know, one of the things that the space shuttle program has done for us. Has really made it possible to do all the future things that we want to do in space, and with a lot of know-how, an unbelievable amount of know-how. And the legacy of the shuttle program, I think, is really the space station. You know, we spent, you know, the last more than a decade building the space station, and there it is. You know, I mean, you fly up to it, and there's another spaceship in the sky as you approach it, and you get closer and closer, and it gets bigger and bigger and bigger and bigger, and it's a massive structure. You know, it's you know, as you know, it's, you know, 2 football fields in size if you lay it down. And when you're inside it, and you look out the window and you look out to the you know, solar panels out on the truss, it's far out there, and there's big solar panels, and this big giant thing that has all the science capability and ability to keep 6 people living comfortably, you know, for months at a time. It's just flying around the Earth, you know, running only on solar power, you know, and we built this thing, you know, with the space shuttle. So I think as the space shuttle retires, you know, I think the legacy it's left behind is really, you know, the foothold that we have now on, you know, everything we can do in the future in space, and the space station is that foothold.
Well, on the subject of legacies and perspectives, you're going to be flying this mission right around the 50th anniversary of the first human spaceflight by Yuri Gagarin,
Right.
and the 30th anniversary of the first shuttle flight,
Yeah.
and close to the 50th anniversary of the first American spaceflight by Alan Shepard.
Yeah.
What are your thoughts about the fact that you are going to be in space while everybody is paying attention to these milestones?
Yeah, it's amazing. I feel very lucky. You know, it's a whole generation of dreamers, you know, like me, who, you know, who grew up on Star Trek, you know, and saw Apollo and watched all this happen. And it's amazing, you know, what we've accomplished in that time. You know, I mean, you can look back 100 years, you know, and look at, I mean, Kitty Hawk, the first powered flight, and you know, in fact, if you look at the, you know, the Wright Flyer, it almost kind of looks similar to the space station in its shape in a way. And the first flight of the Wright Flyer would have only been half the distance of the size of the space station. You know, in 100 years, we've gone from that to this incredible facility, you know, flying in space. So, we've accomplished a lot. I mean, you know, you know, I think a lot of people wish we were back on the moon and on the Mars by now, and so do I. I hope that I would walk on Mars in my career time, but it is amazing how much we've accomplished in 50 years, and it took so many people to make all that possible, and it's an unbelievable honor to kind of be the representative of that generation of dreamers for me.
If we've done that much in the last 50 years, where do you think we're going to be 50 years from now?
Well, I think the key is going to be, you know, the time when it becomes profitable for more than just governments to be operating in space, and you know, and that time is coming. And you know, and once we kind of pass that transition, I think there'll be a lot more traffic. You know, I hope to see. You know, I said I'd like to have walked on Mars in my career time, but maybe I can go as for a retirement vacation someday. You know, but you know, I think we're going to see, you know, many more people getting a chance to fly in space, and you know, I'm sure we'll see bases starting to grow throughout the solar system. You know, starting on the moon, Mars, and first colony, and we'll have the first people born in space, and I think our future history will have more and more happening away from Earth, and that'll be very interesting.